Good day, ladies and gents. Welcome to our next video. We're going to be considering load paths for lateral loads and bracing design. Now, this is a topic where I generally find a lot of students actually struggle to catch on to the concepts, and it takes them a while to appreciate how to do load paths for lateral loads and how to get lateral stability right. But in all honesty, if you want a building to collapse in real life, it's probably because you've got your load paths incorrect. It's one of the more dangerous mistakes to make, and a lot of people don't understand this concept. However, once you get it, it's quite easy to apply. It seems that with many people, once it clicks, they can do it, and then they can continue on from there. But let's see how this goes as we now start heading through the lectures in this section. Here you can see the structure we're going to be designing as a case study in this video. It says, consider the structure shown here and on the following slides. Sketch a bracing system to carry the 10 kilonewton lateral load wind loads shown. Analyze the structure considering the 10 kilonewton lateral loads. For simplicity, notional horizontal loads and other loads have been excluded. And just a couple of things to realize is that this video follows on from 3 previous ones. Firstly, understanding bracing and bending moments in buildings, approximate bending, building analyses, truss beam analogy, and then load paths for vertical loads. And especially with load paths, if you've watched the last one on vertical load paths, and then you can understand how to transfer loads from one part of a structure to another, it'll make your life a lot easier in this video if you can already understand that concept. Now, here's a more detailed view of the structure with the dimensions and showing the different loads, and where we've got a bunch of 10 kilonewton lateral loads. In reality, they all wouldn't be 10 kilonewtons. They would be adjusted for the tributary area of the wind, but here we're going to assume they're all the same just to make things easier. And yeah, very simple structure. We're going to brace it for only one direction, so from loads from bottom to top, so from grid line 1 to grid line 3, and then we've got grid lines A, B, and C in the other direction. Here you can see a real structure, and let's just consider this before we go into our simplified structure. Now, if you wanted to come to the bracing design of the structure, it may seem very complicated. Because I mean, this is very large. You can see a little person down the bottom here. This is about a 12-story building high. And ultimately, though, this can be broken down into a series of two-dimensional analyses using the exact same principles we're about to cover. Here you can see a 3D model of the structure, and it's been put together with all the silos and connections and etc. that one company was fabricating. So this was the fabrication drawings showing everything down to every bolt and gusset plate, etc. in the model. Now, we're not going to get into the bulk of the details, but I just want to show you then the bracing layouts on the structure. First of all, I'm going to get rid of the bulk of the structure and the hoppers, just a little canopy on the one side. Here you can see very sort of traditional cross bracing, horizontal pipe for compression load, and that kept that first bay stable. And then we go to another smaller bay, and then once again traditional cross bracing layout. Then we get to the main building, and here you will see a large braced bay on the structure all the way up the left hand side. The geometry is not perfectly regular because of where the floors were, but very heavy bracing all the way up this left hand side, and within a piece that came out of the top of the structure where the bucket elevators sat, and then there was some more cross bracing, so that load would come down, come to the floor, and then be carried across horizontally through the floor to this section, and then loads would be carried all the way down to the foundations. Now, this braced bay being relatively narrow had very high compression and tension loads when the wind blew on this, or there was a small amount of seismic activity in this area. So you'd had very high lateral loads in this section and very high tension forces in this. You can see some quite heavy connections here that were designed for. Now, moving back further, I'll show you then, you can see bracing for the other direction emerging. So you can see there were multiple braced bays for the loads from the other direction, and then moving through all the floors and staircases, etc., through to the other side. And then I'm just going to cut out the rest of the building here, and then you can see something similar on the other side, that braced bay. So here you go, brace bay on the left hand side. Here, this is actually quite unusual, but we spread the bracing out horizontally. This was simply because the forces were getting a bit high in one area on the foundation, so we tried to spread the load into some of the other columns. Now, coming back to this, so here you can see that we had two specific main brace bays carrying the bulk of the load. And so if I take an end view, it would be on the left-hand side here and on the right-hand side. And all the loads applied to all the faces would be spread across to those braced bays through floor bracing or various other means, and then we would design each of those braced bays. So hopefully that's given you a bit of an overview of practical bracing, and now we're going to go back to our very, very simplified layout to try put this into practice. Here is a model of the structure, and if we load it in the direction in which it's not braced, we actually have a mechanism, and if these were true pins, the structure would fall down. Now, loading it with the bracing, here you can see a zoomed in view and a normal view of the structure, and you can see how as we load it, the one side wants to lift up, the foundation actually wants to lift up in tension, and then the tension bracing carries load while the compression bracing just falls out, buckles out the way. You can see how if we load it at different levels, everything from there downwards is stressed, and then from there upwards is not stressed. And you can also see how when we load different parts of the structure, then different brace bays carry the load. Here you can see a same thing just from a different angle, loading the middle bay, then the load gets transferred to the braced floor bracing and across, loading the side bays, etc. And once again you can see how the braced bay, which we've zoomed in on, when it's loaded, that brace goes into tension. The first thing we need to do for our structure is to sketch a bracing layout. Now, how are the loads, all the lateral loads, going to get to the foundation? And just remember, our braced bays are going to carry the lateral loads, our columns carry the vertical loads. Now, we have the wind blowing from bottom right to top left, so blowing across the structure. And as a structural engineer, we then need to look at the mechanical engineer's drawings or the architect's drawings and then decide where can we put bracing. Where are there doors, windows, machinery, conveyors, equipment? Where are things that we can't put bracing in the way of? And then work around that, and also where are there foundations which we can carry load to if not all the foundations are the same, because we will then need to increase the size of some foundations if there's increased load on them. So in this one I've decided, for instance, that I want to put the load to these foundations. I could have used other support, but I've decided to put it there and there. Those are the foundations I'm going to get all my lateral loads to, and then above those, then I can create a braced bay. So here's a vertical bracing there, and then shown also in plan. And that means now I can take these, this bay and this bay are now stable. This bracing is now very stiff. Relative to the rest of the structure, it is virtually infinitely stiff because everything else we've assumed to be pinned, although in reality it's not. And this will now attract load towards it. However, the middle bay is still unstable. Grid line B, if I applied a load to it, would still fall over. So I need to add more to this structure to try get it stable. Especially, let's say if I started up here, if there was a load applied right up at the top of the structure, I would somehow need to get that load to those foundations. So let's say, for instance, I put a braced bay down 1 story. That will now carry my loads down, but I'll have to spread it across to those braced bays. If I wanted to, I could actually take this brace all the way to the foundation, and then that would sort the problem out. I'd have 3 separate braced bays, and the entire structure would be stable in this direction. However, it would block then the access on 2 floors and would probably get in the way of the structure's operation. So I want to keep bracing on the outside of the building as far as possible, so I'll rather go down and then carry the loads horizontally with floor bracing here and here. And that floor bracing could be a concrete floor, it could be steel decking, or it could actually be physical bracing installed. Normally it's not as neat as I've shown you in real life because there's beams in the way, so often you'd have funny bracing in between those beams, so it looks less elegant but then fits in with the floor beam arrangement. Now once I have this, the entire structure is stable. I can carry loads from every node laterally or vertically down to those foundations. So here's some steps we're going to be following now in carrying out the rest of the analysis. A load path analysis or load rundown will be done starting at the top, and then what we should do is analyze the models furthest from the supports, transfer loads from one model to the next, progressively analyzing the entire structure. Be careful of not applying a load in more than one model. Also make sure you don't miss any loads. So when it comes to applying loads, often a node will be part of two models. So a vertical model and a horizontal model. We only apply the load once. If we apply it twice, we will double account for it and we'll be adding on load that is not there. And then also make sure you know which cross-bracing members in tension and which is in compression, because when it comes to analysis, the tension members carry load, the compression members do nothing. In cross-bracing, in beams and columns are designed for compression and tension, so they can carry both. So here, for instance, is allowed. I'm going to start on grid line B. So that's this middle bay. And let's have a look now. Which loads are we going to apply? Well, I'm going to be just designing primarily this top section, but in reality, it's this whole bay. And so I want to now support the structure, and I'm going to support it at level 2 and level 1 with the floor bracing. So if I push horizontally at this position, the relative stiffness of the floor, because of the combined floor and vertical columns, is much higher than this braced bay, a minimum of 5 times higher, but in this case it's much higher than that. And that means that relatively speaking it adds on a support. If I push horizontally there, almost all the load is transferred horizontally, and vertically it's almost like a giant floor beam or diaphragm, and then vertical brace bays down. So I have supported it laterally. I will now add my 10 kilonewton load on here at the top, and I could add the 10 kilonewton force here and here. There's absolutely no reason why I shouldn't, but you'll see I'm going to add it in later models to reduce the amount of work, but I could do it either way. As long as I don't do it twice, it's fine. So now once this load is applied, it'll put this whole section into compression. That'll then go into tension as it tries to elongate that diagonal, and then after that, to get static equilibrium, that would go into compression as it squashes the other one side and then pulls up on the other. So here we can then have our static equilibrium set out, and we could determine the forces in all those members quite easily. If we now want to transfer the load into our next model, I'm going to call this R1, so a reaction at this position. Sum of forces gives R1 equals 10, so that should be quite easy to calculate for you. And then I will use this R1 in the next model. So here we now have our floor bracing. So I'm designing this section now, and once again, this section is supported by the vertical braced bays. So here and here I have done it. Now I could, if I wanted to, move those supports to the far side. There's absolutely no reason why not. In this model, I'm just being consistent. So if I put the support here, in the next model, I will use that same node. So as long as I'm consistent of if I put it at the front node, then when I do the vertical brace bay, I put it at the front node. Then you're less likely to double account for loads in the members here and here. So now there are my supports from my vertical bracing. I have my R1 load applied at the same node as where I transferred it from the last model, and then my 10 kilonewton load applied here. So now I've added on my second lateral load, and then compression, and then tension. So that is then the load parts, and everything else is a zero force member. And then I will now have two reactions, one each side, and then sum of forces gives 10 kilonewtons each side. And then if I did add a 10 kilonewton force there and there, they would go up to 20, but once again I'm going to apply those in later models now. So now let's continue on with the next floor down. So this is the level 1 floor, and very much the same. I add my third load, I get my forces, compression and tension in all the members, and I get my reactions each side, and they're 5 kilonewtons each. I've kept the structure very symmetric to make life easier, but often these reactions will not be identical. You'd have to take some moments to find those. Now, let's start with the vertical bracing. So I'm going to start then with the left-hand side, and just remember I've got loads from 2 sets of floor bracing and then the lateral loads applied. So once again, there's my lateral loads. I've added on now the next 3, so now I've got 6 loads I have accounted for, and then I've got my second floor bracing, my first floor bracing, and then if I go through that, that will be where I've got compression, and then tension in all those diagonals, compression through the floor members, so those floor beams would also have to be designed for compression. And now I now have reactions as well. So I've got a vertical reaction, a compression reaction here, and then a tension and uplift force there, and then taking sum of forces and sum of moments about this point, I can solve for those and have a horizontal force of 45, which is just the summation of those, and a vertical force from the sum of moments of 68 kilonewtons. Continuing on, we'll swap over to the other side. So there's that brace bay. We're going to continue now. I've got my 10 kilonewton loads. Now I have considered all 8 loads. All of those loads have appeared in one model, not more, not less. And then I've also got my floor bracing, carry out my analysis. You can see which members are in compression and tension. Everything else is a zero force member. I have my reactions horizontally and vertically, compression on this side, tension on that side, and uplift on that side. So this foundation would experience some uplift. And then sum of forces, I would then get to a horizontal force of 35, vertical forces actually of about 44. So that actually takes you a full rundown through the structure, full load path for all the lateral loads. Now, let's just do a quick sanity check. Let's see if our results make sense. If we took the sum of all the applied forces, there were 8 loads at 10 kilonewtons, so about 80 kilonewtons each. Our reactions horizontally, 45 and 35 gives us 80. Yep, that seems about right. Those two match up, so therefore there is horizontal equilibrium. And also, there is more load on the left-hand side, and our reaction on the left-hand side is higher. There's a bit less on the right-hand side, our reaction on the right-hand side is a bit lower. Hence, also the load distribution between the two seems more or less correct, that it's not exactly half-half each side. So it appears that horizontal equilibrium is okay, and what we have done generally seems okay. But let's also compare this with a full 3-dimensional analysis. So here's a very simple finite element model, modeling the whole structure with the same boundary conditions as we had, because ultimately it's actually beneficial to do 2-dimensional analyses. It makes our lives a lot simpler, but we want to know, are we missing something? Are we approximating this in a way that is inaccurate? Well, let's have a look. If I compare the results between my simple models and this finite element model, you can see my horizontal forces here are about 45, and then the reaction is 44.82 in this model. This comes from the results, the output file of this model, but we could also get this if I just convert this diagonal. If I take sum of forces at this node and I get the horizontal component of this diagonal, I will get to that result. So you can see, yep, our results are tying up. Verticals almost identical. There is my vertical force in that member, 67.79 versus 68, almost the same. And the vertical reaction this side is then the vertical component of the bracing plus the vertical the vertical load in the column. And then grid line C, so on the far side, yep, horizontal reactions almost identical, vertical reactions almost identical, showing that there's very good agreement. And then the way we've done this load rundown appears to be correct. Hence, there's good agreement between a simplified analysis and finite element model. However, this is based on the boundary conditions. If we had fixed bases and stiff columns, it would be less accurate. So if we had very stiff columns at the back here, fixed fixities, this would be less accurate, but in all honesty, this is normally sufficiently accurate for what you require to do a load rundown. And also, this is based upon statically determinate structures. If this was indeterminate with multiple braced bays, varying stiffnesses, different floors, it would get less and less accurate. But at least you can see we've done something that's consistent, produced good results, and has been a good way of doing this analysis. So hopefully that has given you an overview of how to do a load path rundown and a bracing analysis of structures. Thank you.